Okay, this is section 2.4. We're doing more differentiation formulas. Specifically, we're going to be focusing today on the differentiation formulas for trig functions. And there are 6 of them. So there's really just 6 things to know. But we are going to actually go through at least why some of these things are the derivatives that they are. Ultimately, at the end, you're just going to need to kind of know these. You're going to need to memorize them, because trying to figure all this stuff out by, solving it algebraically or something, it's just going to take too much time. So the best option is you're just going to need to know these. I did say, however, that in a previous video, because we've actually talked about what the derivative of sine and cosine are, that I would at least prove one of them. I'm going to prove one of them for you guys, and the other one I'm not going to prove, but it would be basically the same general idea. Okay, so let's start off with the fact that we already have talked about the derivative of sine and cosine. We do know that the derivative of sine is cosine of x, and we know that the derivative of cosine is negative sine x. This part here is not going to be a proof, but it's going to be more of a visual representation of what's actually happening. So remember that sine, the graph of sine, is a wave that starts here at the origin, and then it's going to go up to its max, come back down, go down to its min, and then go back up. And then remember, technically this keeps on going forever and in both directions. While I'm not going to use those parts, does something like that, and it keeps on going, like I said, forever. So it would just keep on going. The important part here is that I want to kind of focus on, so we know that that's at 0, we know that's pi halves, we know this is pi, this one is 3 pi halves, and this is 2 pi. So that'll at least take us through one full circle, or one full cycle of sine. So the general idea is, if you're going to take the derivative of something, you're looking at its slope. Well, there's a couple of places on here where the slope values are pretty obvious. Here it looks pretty obvious that we have a slope of 0, and here it looks pretty obvious that we have a slope of 0. So when I go down here, I'm going to graph the derivative of sine of x. So if I graph the derivative of sine of x, I do know that at pi halves and at 3 pi halves, I should have a value of 0. So this right here is f of x equals sine of x, and then this down here is going to be f prime of x. And we know that's supposed to be cosine. Well, that's, again, we're going to visually see that. So if you were to take a look at the slope of sine, or of our green function up at the top, at 0, this piece right here, if we were to find the equation of the tangent line right there and look at that tangent slope, would be 1. So when I come down here, I'm going to graph a y value of 1. Over here at pi, the tangent would be a slope of negative 1. So I'm going to come down here at pi, and I'm going to graph a slope of negative 1. And then, as you very well might have guessed, the slope at 2 pi, because it's really exactly the same as what it is at 0, the slope there is a slope of 1, which puts the y value of the derivative at 1. And then if you were to do all the slopes in between, which I'm not going to draw, you would get this general looking curve, which we know to be the cosine curve. And then if you were to do the same thing, which I'm not going to graphically do, but if you were to do the same thing with cosine, you would actually get the sine curve that you see up there in green, but it would be negative. It would actually be flipped over the x-axis. It would be a reflection. So again, that's not a proof. It's just a graphical representation to hopefully give you somewhat of an idea that these two things are the derivatives that we say that they are. So let's go ahead now and look at, because we have 4 other trig functions. We have to figure out what the derivatives of those 4 trig functions are. And if you know the derivatives of sine and cosine, then we can easily figure out the other ones using the quotient rule. because all other trig functions are some kind of a quotient of sine or cosine. All right, so let's talk about the derivative of tangent. So the derivative of tangent, we can write tangent, first of all, as sine over cosine. So really what I'm going to take the derivative of sine of x over cosine of x. That is clearly a quotient. We can use the quotient rule now to simplify this. Quotient rule says the derivative of the top, which we now know is cosine of x, times the bottom, which is also cosine of x, minus the derivative of the bottom. Derivative of the cosine of x is negative sine of x, times the top, which is sine of x, all over the denominator squared. So just so that you know, and because it gets confusing, cosine squared of x, this is the same thing as cosine of x, the whole thing in parentheses squared. They mean the same thing. Or you could write it technically as cosine x times cosine x. Okay, those all mean the same thing. The only thing you can't do is remove that parentheses and put the squared on just the x, because that means the angle is squared. In this case, the whole trig function is being squared. We put the 2 in between the s and the x so that you don't have to worry about that parentheses. That's why the squared is in between the s and the x, so you don't have to worry about the parentheses. All right. Continuing to simplify, on the numerator, we get cosine squared of x. The minus minus becomes plus, so we get sine squared of x over cosine squared of x. Cosine squared of x plus sine squared of x, these are one of the Pythagorean identities that we absolutely must know, is 1. So it's 1 over cosine squared of x. And yes, that is the derivative of tangent. It's not the most common form we're going to see it in because the reciprocal of cosine is secant. So 1 over cosine squared is the same thing as secant squared x. That is the derivative of tangent of x. Okay, again, that's something you're going to need to just know. You're going to need to memorize that. Okay? While I would love to go through the proof, I think it's not worth our time. The derivative of cotangent of x, this might be something you want to try on your own to make sure you can actually do it. Well, cotangent is obviously cosine over sine. It's still going to be a quotient rule. And when you eventually do that, you will end up with the negative cosecant of x. That's the derivative of cotangent. Okay, again, you can do that by using the quotient rule. We, however, are going to skip to the next page, and I will prove one of these two. As a matter of fact, I'm going to prove the secant one. I'm going to skip cosecant. I'm going to prove the secant one here. Now, remember that secant is 1 over cosine, so they mean the same thing. So we're going to take the derivative of 1 over cosine of x. Once again, you can use the quotient rule. So the derivative of 1 over cosine of x. The derivative of the top, well, the derivative of the top is 0, times the denominator, cosine of x, minus the derivative of the denominator, which is negative sine of x, times the top, which is 1, all over the denominator squared. Let's simplify. 0 times cosine is 0. I've got a minus minus the sine of x, so that's plus. So we're just going to get sine of x over cosine squared of x. And again, that is going to be your derivative, but we want to simplify this so it's non-fractional. So what we're going to do is we're going to split the denominator to be cosine x cosine x. And the reason we want to do that is because now what I can do is I can split this to be sine of x over cosine of x times 1 over cosine of x. And sine of x over cosine of x is tangent x. 1 over cosine of x is secant x. So the derivative of secant x is tangent x secant x, or secant x tangent x. The order doesn't matter because they're being multiplied. And if you're really thinking about it, if you're kind of following how these patterns are working out, you could probably guess what the derivative of cosecant x is. It's very similar to this one. Instead of having tangent and secant in it, it's going to have cosecant and cotangent in it. And as a matter of fact, it will be cotangent x, cosecant x, but it will be negative. Again, that is something you could do by starting off with 1 over sine of x instead of cosecant x, and then performing the quotient rule. All right, so there are your 6 trig function derivatives. Whatever way is best for you, you definitely just need to know these. You just need to have these as quick recall. They are relatively easy to figure out and to be able to solve. At least the last 4 are, assuming you know the derivatives of sine and cosine. But you don't want to spend your time doing it. You just want to know these. Couple of things to help you out. There are several ways that you can go about memorizing these, assuming, again, you know the derivatives of sine and cosine. Any function, any one of the trig functions that has a co in it, or basically begins with a c, meaning cosine, cosecant, cotangent, all of those derivatives are negative. The other derivatives are positive. So that should help you with the sign. So anything with a c, anything that starts with a c, or has the word, or has the prefix co in front of it, those trig derivatives are negative. The other 3 are positive. As far as the tangent and the cotangent derivatives, this really comes to, if you remember which functions go with which other functions when it comes to the Pythagorean identities, tangent and secant go together. The tangent squared and the secant squared go together. So when you take the derivative of tangent and you get secant squared, sometimes that's an easy way to remember it if you remember the Pythagorean identities. If you don't, again, just memorize this whatever way is easiest for you. And as far as the cosecant and cotangent, the cosecant and secant, the one nice thing about those is, again, the cosecant and cotangent, those go together with Pythagorean identities, and the cosecant and the secant, as you can see, they each have themselves in the derivative. Cosecant has a cosecant in it. Secant has a secant in it. That's kind of nice that they have themselves, and then you just have to remember that they also have the other piece attached to it. So again, whatever way helps you. I just threw out a couple of things that I know that helped me when I was trying to memorize them, but just know them. All right, let's go ahead and look at some examples. So we're going to kind of piece together some of these things that we've been doing. So now we're incorporating not only the derivatives of our trig functions, but we're going to have products and quotients and all kind of other stuff going on. So we have to incorporate everything that we've learned so far. All right, so the derivative of f of x, where f of x is x squared tangent of x. It is a product rule. I have x squared times tangent x, 2 functions. So the product rule says, when I take the derivative of the first term, which is 2x, multiplied by the second term, excuse me, plus the derivative of the second term, the derivative of tangent x, and I don't expect you to have it memorized that fast. It is secant squared x. Eventually, you will just know this. Times the first term, x squared. Only thing you should do now is kind of clean it up. Move the x squared out to the front of the secant squared. Again, we typically put the polynomials out in front of the trig functions. So that would look like tangent 2x tangent x plus x squared secant squared x. This also helps for future purposes when you might have to do some kind of other work with this stuff, maybe factoring out an x or something like that to solve some equations or something later. Just helps from that perspective. Okay. All right. The derivative of number 2, y prime. Again, 5x and cosecant x, 2 functions. Excuse me. So the derivative of the first is 5 times the second, cosecant x, plus the derivative of the second one. The derivative of cosecant was negative cosecant x cotangent x. Times the first function, which is 5x. And then again, we're just going to clean this up a little bit. So it'll be 5, oops, that's an s, cosecant x. We'll move the 5x and the minus sign to the front. Cosecant x cotangent x. One other thing I want to point out when it comes to this, again, you must have an angle. Leaving the x off is going to cost your mathematics and cost points, because if you were to write CSC COT, that means nothing. Even if you put CSC COTX, that technically means you're going to take the cosecant of cotangent of x, where cotangent of x would be the angle of cosecant. You must include the angles. Okay, do not drop the angle. Do not drop the x or the theta or whatever we put there. Must be there. All right, we got a couple where we're going to use the quotient rule now. So g prime of t is going to be the derivative of cosine, which is negative sine of t, times the bottom, which is t, minus the derivative of the bottom, which is 1, times cosine of t, which is the top, all over the denominator squared. So again, let's just clean that up a little bit. We'll move the t to the front of the negative sign area, so it's negative t sine t, minus 1 cosine t, don't need the 1, over t squared. And remember that you cannot cancel an angle. Okay, you cannot cancel the t's out of the angles or something like that. That does not work. So that is final. That is about as clean as we're going to get that one. Technically, you could factor a negative out, but there's really no reason to do that right now. All right, and then the last one here. This one's going to be a little bit longer to simplify because I want to show you how this thing simplifies all the way down. F prime of x. The derivative of the numerator is cosine x times the denominator, minus the derivative of 1 minus cosine x. The derivative of 1 is 0. The derivative of negative cosine x is actually going to be plus sine of x, times the numerator, sine of x, all over the denominator squared. Now, how you go about this, the rest of this, some people come up with a different way. I'm just going to do the first way that I can think of. I'm going to go ahead and distribute the cosine. And then on the end there, I'm going to have a minus sine squared of x, all over 1 minus cosine x squared. Again, no reason to FOIL that out in the denominator. It will probably make simplifying harder later. Okay, what I can do on the numerator is I can factor the negative out of both the cosine x and the sine squared of x, and putting that in parentheses, that leaves me with a cosine squared x plus sine squared x all over 1 minus cosine x squared. Now, if you're not sure what I just did there, really take a look at what would happen if I were to distribute the negative from this specific line right here. If I were to distribute that negative back through, it would just give me what I had in the previous step. Because a lot of people are like, you can't factor something out of just 2 terms. Well, you can, as long as it doesn't affect the other term. So all I did was I factored the negative out of the cosine squared and the sine squared, which then left the negative on the outside of the parentheses, giving me a cosine squared plus sine squared. The reason for that, obviously, is that we want that to be 1. So cosine of x minus 1 over 1 minus cosine of x squared. I can then go ahead, because I notice cosine of x minus 1 and 1 minus cosine of x are completely opposites. I can factor the negative out of the top once again. That's going to leave me now with a 1 minus cosine of x over 1 minus cosine of x squared. Well, now I can get rid of one of the 1 minus cosine x's on the top and the bottom, and leaving us with the final answer of negative 1 over 1 minus cosine of x. Technically, you could throw that negative sign on the denominator and make it positive 1 over cosine of x minus 1. Either one is perfectly fine, but that is the most simplified answer. Taking you all the way back up to this part right here, technically, that was your derivative. If you don't have to simplify because there's nothing else to do and you're just supposed to find the derivative, leave it like that. Most likely, you'll have to do some simplification to match an answer, though. All right. I think that we will come back with a second video. The second video will have, let's see, what are we going to be doing? We're going to find the derivatives of the functions on here, and then I'm going to go through the proof that sine of x is actually, derivative of sine of x is actually cosine of x.